It's cold out there. If you live somewhere with winter, then you know exactly what I mean. But if you go outside without a jacket, you will also know that it gets really cold very quickly. And I'm not talking about the kind of cold where you just feel a little bit chilly. I'm talking about temperatures below 273 degrees Celsius or negative 100 degrees Fahrenheit. That is the temperature of outer space. And for all we know, you might be floating around in the middle of space right now. Because if you're rewatching this video, you're probably not paying attention to whether you're standing on the ground or not. So please pay attention. When you stop paying attention, you fall over. But enough about falling over. Let's talk about something that's not falling over but should be. The planet Uranus doesn't give off enough heat. Scientists have been noticing this since they first observed the sideways planet back in 1781. They've noticed that it didn't seem to emit much internal heat. In other words, it was strangely cold. And by strangely, I mean so strangely that it's been baffling scientists for centuries. You see, most gas giants like Jupiter, Neptune, and Saturn radiate more heat than they receive from their host star. For instance, Jupiter radiates more than twice as much energy as it receives from the Sun, which is pretty impressive considering how far away it is from the Sun. Meanwhile, Uranus seems to only emit as much heat as it receives from the Sun, which is surprising given that it's twice as far away as Saturn, which gives off so much more heat. Okay, so you're probably thinking, what's the big deal? There's a perfectly reasonable explanation for this, right? Well, yes, but no. You see, the leading theory for why Uranus has such a low amount of internal heat is that it experienced a giant impact early in its life. This would explain why it's on its side, but it would also explain why it isn't radiating as much heat as it should. Basically, when two objects collide, some of their internal kinetic energy gets converted into heat and then radiates away from the point of impact. Scientists think that's what happened to Uranus. Something big crashed into it long ago and knocked it on its side, while also bleeding away a lot of its heat. And that may be the end of the story. But another team of scientists thinks they've found evidence that points to a different culprit behind Uranus's missing heat. Instead, they say that Uranus might just be made out of stuff that doesn't hold on to heat very well. Now, that may sound kind of ridiculous. After all, Uranus is mostly hydrogen and helium, the same stuff that makes up Jupiter and Neptune, and those planets have plenty of heat. But here's the thing. It's not just the composition of a planet that matters. It's also how that stuff is mixed up inside the planet. In other words, it's the same old story. It's the convection currents. Stupid. Just like our oceans, the insides of gas giants are made up of fluid layers that circulate. Hotter, less dense fluid rises, while cooler, denser fluid sinks. But unlike Earth's mantle, the interiors of the planets in our solar system aren't solid. They're all in varying states of gaziness. And that makes these circulation patterns way more complicated. Because just like you cut into mix oil and water, different gases don't mix together easily. For example, hydrogen and helium have very different densities and will tend to separate over time. And the deeper you go inside a planet, the greater the pressure and temperature. So as gases get deeper and deeper, they'll eventually become part of a layer that's hotter and denser than the one above it, causing them to sink. Then when they reach the bottom of that layer, they'll start to cool off and rise back up to the surface. Now, if those gases were perfectly mixed, this process of rising and sinking would be pretty quick and efficient. But if they're not perfectly mixed, then the result is something called a dead zone, a layer where gases just kind of sit around and don't mix with anything above or below it. And that could help us understand why Uranus is so cold. Researchers have been studying the internal structure of Uranus and Neptune using a technique called so let's talk about some of the stuff they learned. Uranus and Neptune both have a thick atmosphere of hydrogen and helium, just like Jupiter and Saturn. But unlike Jupiter and Saturn, the hydrogen in Uranus and Neptune's atmospheres is really diluted. To illustrate how diluted, researchers ran computer simulations of these planets' atmospheres to try to recreate what's happening inside. Their models revealed that Uranus's atmosphere would need to have been 50 times more massive for convection currents to have properly mixed the hydrogen and helium together. But that's not the whole story, because even if Uranus had more hydrogen in its atmosphere, it still wouldn't do anything unless that hydrogen got deep enough to reach the planet's interior. And there's evidence that suggests that Uranus's interior might have a giant dead zone, a region of stagnant, unmixed gases that could be blocking the flow of heat from the planet's core to its surface. The researchers aren't quite sure yet how deep this dead zone goes, or exactly what is causing it. But they hope that future observations can shed some light on this. For instance, the James Webb Space Telescope should be able to measure how much heat Uranus gives off. This will help scientists figure out if the planet's giving off as much heat as its atmosphere should be, or if there's something else going on down below. So did Uranus lose its heat because it experienced a giant impact early in its life? Or is there something weird going on in its atmosphere? Maybe it's a combination of both. As always, more research is needed. I'm glad you asked. We have seriously upped our video game with this new series, all thanks to our supporters. By joining the team, you'll get access to a ton of perks like bloopers, deleted scenes, and even live streams. Plus, your name will appear right here forever. Okay, maybe not forever, but at least until the heat death of the universe. Join us at our website,